So I thought this would be an opportunity to say where we've been, um, knowledge-wise, and where we are today. So this is what they used to think the universe was. Concentric circles. They like circles. Circles were perfect, so they like doing circles. Earth, of course, is at the center of the universe, and then you have a different sphere for each of the planets, and then one sphere for all the stars. All the stars are in another sphere called the firmament. And then after that, there's three more. Those are the spheres that control the movement, the crystal spheres that cause the whole thing to move. In fact, here's an early explorer, I guess, popping in to those other spheres and seeing the gears turning everything. Here's the firmament with all the stars all in one plane, one sphere. Putting the Earth at the center of the solar system causes problems because the other planets don't move right. So the sun's moves right. The sun's okay because it appears to be moving around Earth. But the other planets all require these things called epicycles. So they're actually, not only they're going around orbit around the Earth, but they're also doing these little twirlings in space. That's to get them to look right. Otherwise, they won't look right if you put Earth at the center. If you move the sun to the center, then they look right. There's what we believe now, though. We believe we live on a sphere called the Earth. We're about there. And that the sphere has a companion we call the moon. Unfortunate name, because we started using the name moon for a generic word meaning satellite of other planets. So we talk about the moons of other planets. Well, they're not the moons of other planets. They're satellites of other planets. So maybe we need a new name for this thing. We could go back to the Latin. These two are really a dual planetary system, because if you look at the other planets, well, Mercury and Venus don't have moons. Mars has two small moons called Phobos and Deimos, but compared to its size, they're small. And then Jupiter and Saturn have moons, but they're big. Now you can compare them. You could compare them to our moon and stuff, but they're bigger planets. But this one, these two are closer in size. So a dual planetary system wouldn't be a bad thing to think of it. And of course, they're part of the solar system. And it's called solar because this thing in Latin is called, the sun is called Sol. So it's a solar system, and it's got 4 rocky planets. The 4 rocky planets were the third one. And then there's an asteroid belt, which is kind of a failed planet. It was kept from forming by the gravitational pull of Jupiter. And then we got 4 gas giants. Only 3 of them are shown here. Neptune's missing, would be the outer one. Then there's something called another rocky belt called the Kuiper belt. Pluto's in the Kuiper belt, but there's a bunch of other Kuiper belt objects also besides Pluto. And then on the outside of that is something called the Oort cloud. And the Oort cloud is kind of like almost like a halo. And all the comets are there because the comets are in orbit around the sun also, but they have, some of them have extreme long periods of orbit, like, 500 more than thousands of years. So that's the outer Oort cloud, and that's the end of the solar system. The solar system is part of, there's a local group of stars. These are our neighbor stars. Notice how many of them are red dwarfs. By the way, it's dwarfs. It's by convention, you have white dwarf, red dwarf, brown dwarf. You don't change the V to a V. You don't change the F to a V and put an ES on it. You just put an S on the F after the F. But look how many of them are red dwarfs all over the place here. These are our neighbor stars. I mean, we have stars that are the same as ours, like the Alpha Centauri system. This one's Tau Ceti down here. But still, look how many of them there are. And of course, this is part of the Milky Way galaxy. And there's our galaxy. There's like 4 different galaxy shapes. And one of them is called a barred spiral, where obviously it's a spiral. And it's got the center is a bar versus just a circle. That's another shape. The sun's not even near the center. It's off on the outskirts. Out in the boonies, we're out in the boonies. This is usually referred to as Orion's arm. And on edge, that's looking at it face forward. On edge, it looks something like this, where we have a disk, we have a center bulge, but then there's also this halo, which is full of globular clusters of stars. Globular clusters are collections of stars. That's part of the local group. I know, a real imaginative name, right? The local group. These are local galaxies. The big ones are Andromeda and Triangulum. But there's also of note are these down here, the small Magellanic Cloud and the large Magellanic Cloud. Magellanic from Magellan. Magellan, when he sailed around the world, when they first went south of the equator, they saw these. They're visible to the naked eye in the southern hemisphere. So they got named after him. These are all blue shifted. They're all moving towards us, so their spectrums would all be blue shifted. And the local group is part of what's called the Virgo supercluster. This whole thing. These dots, every dot here is a galaxy. These aren't stars. Each dot's a galaxy. And here's our local group, but we're part of this Virgo supercluster of galaxies. And the universe looks like this. Again, the dots are galaxies, not stars. And they form these filaments. The galaxies seem to collect and form these filaments with these big holes in space where there's nothing, like here. And then these filaments fill in. The large scale picture looks like this. This was mapped by scientists at the University of Hawaii. That's why it's got a Hawaiian name, Laniakea. And these are all galaxies. And they're not even dots. They're too, in this picture, they'd be too small to show as dots. Milky Way's be over here. We're not even at the center of this thing. So, kind of pretty. So that's where we're at. Where are we going? Well, it's based on some scientific principles that are fairly, they're more like logic principles. They're not real difficult. One is homogeneity. And that means on the large scale, local universe has the same physical properties throughout the universe. So we can expect the same physical properties everywhere. Homo means same, gen means kind. So it's same kindity. Everything's the same kind everywhere. So same physical property, meaning like stuff like mass density, expansion rate, visible versus dark matter, that wherever you go in the universe, it'll be the same. And isotropy on large scale, local universe looks the same. Everything looks the same in every direction is what we see. So wherever you are in the universe, you could look out and you'd see the same thing we see. And again, iso means same. I guess this one's Latin and this one's Greek, I think. Maybe the other way around. I don't know. I can't be sure, but they both mean. I know they both mean same. Homo and iso both mean same. And finally, the last one is universality. The laws of physics are the same everywhere in the universe. So all the stuff you've learned about the conservation of momentum, the conservation of energy, the conservation of mass, the conservation of charge. Charge needs a charge carrier. If I put a magnet in a coil, if I move it, I get electricity. Stuff like that. That's all. That should be true everywhere in the universe. If I take a pile of carbon, it's not 12 atomic mass units, it's 12.01 because I have to account for the same percentage of isotopes. So the percentage of carbon-13 versus carbon-12 everywhere in the universe should be the same. Stuff like that. We make that assumption. Okay, so then where are we going? Where are we going? There's two possibilities. Two. One, we started in a Big Bang, a singularity, and we started expanding. And we're still expanding. In fact, we're accelerating. So do we keep expanding forever? Or at some point does the expansion reach a maximum and then turn around? So you kind of like go out and then come back. Are we coming back? Are we going to crunch back down? In fact, it's called the Big Crunch. Back down to a singularity like we started with the Big Bang, only now it's called the Big Crunch. Which one is it? Well, it depends on whether we have a closed universe or an open universe. Do we have a closed universe or an open universe? We don't know. Here's why. So shape is destiny. So we've got three possibilities for shape. We've got three possibilities for shape. Either we're flat, the universe is flat, with no curvature whatsoever. Okay? Or like that. Looks like that. Or it's closed surface, which is also called positive curvature, or open surface, which is negative curvature. Unfortunately, it's sort of like open kind of. Open has the word has a positive feel to it, and closed has a negative feel to it, but then the things are different. So they kind of like don't quite match up with each other, right? So closed universe is positive, and open is negative. So let me show you what they look like. So this is a closed universe. This is a positive curvature, like a ball. It's positive curvature. This is an open universe. This is a negative curvature, like a saddle. That's called negative curvature, because we're kind of like going out, and this one we're kind of like going in. So I guess this is I don't know why negative, why positive. I mean, it's mathematical. I mean, the reason's mathematical. Why can't we tell? Well, we're like a little ant on an orange. You can't even tell the Earth is round from standing on it, but it is. And the universe is even worse. And remember, it's in 3 dimensions. So it's like that. So you can't really tell because we're just too small, and we can't really look at it. So going back to this guy, we can have, is it that? That would be the closed surface. That would be the positive curvature. Is it that one? That's the flat one, no curvature. Or this one, is it the open universe with negative curvature? Which one is it? How would you even be able to tell? Now you can tell it's a round planet. We can't tell it's a sphere. And the best demonstration I saw of proving that it's a sphere was some of the flat earthers trying to prove it's flat. They actually succeeded in proving it's a sphere because there's up in the Central Valley, there's this infamously long canal. It's like a mile or more long, and so it's full of water. So water's going to all be level, and it's long enough that should show the curvature of the Earth. So if you took a laser a powerful laser, and you held it like 3 feet above the ground, above the water, and you turned it on a mile away, according to the flat earthers, it should be 3 feet above hitting a target. If the Earth were round, it's going to hit higher than 3 feet because the laser went straight while the Earth curved. And they did that, and guess what? The laser was higher than 3 feet. So they proved the Earth was round. Good, because they don't accept the pictures. So this is another problem. So besides not being able to tell what the shape is, we don't know what this stuff is. We know this is this 4% here. This is the stuff you studied in chemistry. These are all the stars and the galaxies and everything. And everything you studied in chemistry was this matter. We have dark energy, which we heard about from Reese. Remember, I had you read the article by him, and he determined the universe is not only expanding, the expansion is accelerating, and well, if we have acceleration, we have to have some kind of force behind it. And so he said, he called it dark energy, or they came up with the name dark energy. They might as well have said mystery substance number 1, because that's what dark energy means. We don't know what it is. They could have used mystery energy, whatever. We just have no idea what this stuff is, but it's causing the acceleration of the expansion. Then there's this stuff. This is dark matter. This is mystery substance number 2. This is what's causing the galaxies to stay in night-tight little spirals. Otherwise, they just spiral out. They're spinning. The galaxies are spinning, so they should be like, but they're not. They stay in nice, tight little bundles. And there's another. This is also accounts for something else. We don't know what this is. They're close to determining what this is. Of course, I could be sitting here in 100 years telling you they're close to determining what this is, and still they won't know. But it's hard to make those kind of predictions. It's dangerous to make those kind of predictions. But dark matter, the other thing from dark matter is something like this. This is gravitational lensing. That curvature there is caused by gravitational lensing, probably from this thing. But to make that much curvature, it should be 10 times bigger than it is. So this has to have a bunch of dark matter in it to make it 10 times as massive. So that's another thing about dark matter. It's causing stuff like that. So which is it? Is it open? Is it closed? Or is it flat? Well, if it turns out to be either open or flat, either of these two, if it's either of these two, the universe will keep on expanding forever. If it's this one, at some point it'll stop expanding and then start compressing or shrinking back down, back into a singularity in the big crunch. So this one would indicate the big crush. These two would indicate that it expands forever, but we don't know which one it is. So for your notes, the shape of the universe will determine the ultimate fate of the universe, the shape. And there's 3 possible shapes. You could have a closed shape, that was the positive curvature, the saddle shape thing. I'm sorry, this is the round one. Sorry, this is the sphere. The positive curvature is the sphere. The universe is finite, and a big crunch will result. The flat universe, or the open surface, which is that saddle-shaped one, and the universe is infinite and will expand forever. It also depends on the total mass, which depends on what the dark matter and what the dark energy are, which are not understood. So go ahead and add that to your notes. Now, I think it's flat, by the way. I think we're going to expand forever. If it does expand forever, eventually all the matter gets converted to energy, and all the energy is converted to thermal energy, which was the least defined one, and it just kind of keeps spreading and spreading and spreading out and spreading out till nothingness. Even the black holes, according to Stephen Hawking, one of the last things he wrote about, they'll evaporate. It'll take a gazillion years, but they will all evaporate. So kind of a blah ending, huh, for the whole thing. I think if I will